With regards to negative feedback loop and multiple poles, this is what we were discussing yesterday. Now, the stuff that we didn't discuss in detail was this. A fair amount of detail was when we connect our negative feedback loop like this, right? So this is, let's say, V naught. This is V naught over K. Is the sense of the loop right? When I say sense of the loop, I essentially mean that when you go around the loop, do you think it's a positive feedback or negative feedback? So let's do that quickly. So let's assume that you break the loop anywhere. I choose to break the loop, let's say here, and I apply an input. If this input goes up, what happens to V naught? If that node voltage, some disturbance causes that node voltage to go up, what will happen to V naught? See, you have these things here. So V naught will go up or go down? It will go down, right? So V naught will go down. So V naught over K goes down. So this voltage goes down. So what happens to, assume the loop is broken. So what happens to this voltage? Goes up, right? So the sense of the loop is not correct. It's in positive feedback. It's in positive feedback because how did it suddenly become positive feedback? Because you are having another inversion here. There are two sets of inversions. One through the main, through the main GM, another to the second stage GM, because you have two common source stages now, equivalent to, right? You have two inversion stages put in negative feedback. So essentially, when you go around the loop, it becomes positive. So the thing that sometimes students get tripped over is the fact that just because we have made this a negative sign does not imply the loop is, if you connect everything to that negative sign, it will be negative feedback. It will be negative feedback if and only if you go around the loop and you see that there is inversion happening, right? So that negative sign in this is only pertaining to the condition that if this voltage increases, what is going to happen to this voltage? Right? So that sign is only limited to the block, not the loop, right? So loop can have its own settings. So now, this is a differential amplifier. We know this is a differential amplifier and which is kind of symmetric. You can apply the input at either side of a differential amplifier. So if this is negative, this is not a negative feedback. All we have to do is to flip the places where we apply the inputs, right? So what I'll do, I'll simply say that I'll flip this. This becomes plus, this becomes minus, and now your loop is in negative feedback. Okay, fine. So that is one. The second thing is the stuff that we discussed yesterday was assume that it's driving a capacitive load. Let's say this is C1, this is C2. And we would like to find out the loop gain and the pole locations. So in order to find out the loop gain, we do the same old. We break the loop, desensitize the input, and find out the return voltage. Okay. So if we do that, we see that this voltage will be is equal to V test times, this is GM, times GM negative of that divided by SC1 plus G01, where G01 is the output impedance of the first stage. And V0 will be this voltage times the gain of the second stage. Now, gain of the second stage is minus GM7. Sorry, in this case, sorry, this is not minus, it's plus, right? Because I have applied V test to the positive terminal. So gain of the second stage is GM7 over whatever the resistance that has been attached to it. And I club all the resistances into G2, right? So G2 is all the cumulative resistances attached to V0, and the capacitance attached here is C2, right? So now your And you have negative sign here because the common source second stage has a negative, has an inversion inbuilt, which means your L of S is GM, let me call it GM1, GM7 by, if I take out the G01 and G2, 1 plus G01 over 1 plus SC1 by G01 times 1 plus SC2 by G02. Okay, so this is the DC gain. This is the DC gain, and this is essentially the product of the DC gains of the two individual stages. That should not surprise us. If the capacitances are not there, the gains of the two stages will get multiplied because they are put in cascade. But because of the capacitances, we get two extra poles. Now, if these poles are okay, before I get into two extra poles, we don't I mean, if you think about it, this, we don't even have to write out the loop gain expression to find out where the pole locations are, because as we were discussing yesterday, the pole associated with C1 is essentially the 1 over the time constant associated with that. Now, if I see that what is the time constant associated with C1, if I look at that particular block in isolation, right? So it becomes G01 by C1 or inverse of that. Okay, so the pole becomes at G01 at C1, G01 over C1. Similarly, if I concentrate on what is the resistance associated with C2, it is G2, right? Or I mean, yeah, we have been calling it G2. So the pole associated with that capacitance will be G2 over C2, right? So you can just look at the capacitances and find out whatever is the equivalent resistance attached to the capacitance, Thevenin equivalent resistance attached to the capacitance, while ignoring all the other capacitances. And then whatever you get, inverse of the time constant is essentially the pole. Okay. Yes. Right. So what I mean is, so let's say I have only R's here and non-memory elements, right? You can have control sources, but let's say only one capacitance attached, right? So what will be the equivalent resistance? We find out the Thevenin equivalent resistance here, right? And the time constant will be RTH times the C, right? So the pole associated, first order circuit, the pole associated will be at -1 over RTH times C. Yes. So there are multiple nodes, and yet each node you have one capacitance attached to it. So what are we trying to do? We are trying to figure out what is the equivalent resistance attached to that node, right? So let's say I am trying to figure out what is the equivalent resistance this capacitance is seeing, right? What is that capacitance seeing any resistance attached here? It's not seeing, right? Because ultimately GM7 is shielding it, right? It's for as far as this capacitor is concerned, this part of the circuit doesn't matter. Yes, right? Because looking here, you have infinite resistance, right? So whatever is the left side of the capacitance matters. On the left side of the capacitance, I only have G01. So the time constant becomes C1 over G01. So the pole becomes at G01 over C1. Similarly, at C2, the same thing, right? So when we are doing C2 is not seeing anything, what is happening at this part of the circuit. When I'm evaluating the time constant associated with C2, I'm rounding the inputs and all. So for the purpose of C2, this node is grounded. Then it really doesn't matter. Okay. Okay, fine. So now the important part that we were discussing in the last class was, if the multiple poles P1 and P2 are close by, which it will be, because now your output resistance, your G0s are of the same order, G01 and G02 of the same order. And if you don't put explicit capacitances, C1 and C2 will also be of the same order. And let's take some numbers. So let's say your G01 and G02 are approximately 100 microsiemens. C1, C2 approximately 1 picofarad, right? So essentially, let me make it even simpler, 1 millisiemens. Okay. So G01 over C1 essentially becomes 1 gigaradian per second. And G02 is also, G02 over C2 is also 1 gigaradian per second. So this is, let's say, 1 gigaradian per second. Okay. And let's say the DC gain for each of the stages are 20 dB, 20 dB, something like that. So this is 40 dB. Okay. And after that, you hit 2 poles, which means you have 40 dB per decade roll-off. So where will this hit? Where am I going to hit UGB? So I'm dropping 40 dB in 1 decade. So this will be at 10 gigaradian. Okay. So if this is the 10 gigaradian per second, approximately what is the phase margin? Very close to 0, right? Because we have hit 2 poles way before 1 gigaradian per second, way before 10 gigaradian per second. Each of these poles are effectively going to give you almost 90-degree phase lag. So 180 minus 90 almost equal to 0. It would probably be 1 degree or something or 2 degree, but that's useless. So the next thing then to say is that this is an useless system. How do we make it useful? We have seen that in order to make it useful, we have to ensure that the poles are far apart. Poles have to be split. And around UGB, it has to have a 20 dB per decade roll-off. So now poles are associated with time constant are associated with R and C. So we have 2 handles. We have to either influence the C or we have to influence the R. The R we cannot influence because ultimately the low frequency gain, if I influence R, if I increase R, if I cannot reduce R. If I reduce R, then 40 dB will reduce from the DC gain is going to go down, right? So what is the DC gain? DC gain is this term. So I cannot, GM1 and GM7, I have figured out, I've been using, by burning some power. Similarly, G01 and G02 ideally should be 0 in order to get infinite DC gain. But assuming that you have done the best you can do, and G01 and G02 you cannot reduce further, which means you have maximized the DC gain. If you have put in so much of effort to maximize DC gain, you don't want to compromise and lower it now. So essentially, you cannot then play around with R. The only thing you can play around is with capacitor. Now, you cannot reduce capacitance because all these capacitances come with the device, right? The only handle then that you have is the increased capacitance, right? So I have 2 poles here, one at G01 by C1, another at G02 over C2. I cannot touch G0. I cannot reduce C. The only thing I can do is increase C by putting an explicit capacitor. That we can do, right? So let's choose to put an explicit capacitance in parallel with C1, right? So if I choose to put an explicit capacitance in parallel with C1, C extra, let's say, or let me call it CC. It's called a compensation capacitance. If I put this extra capacitance CC, then what's going to happen? This pole, the first pole, or this pole is going to move to G01 by C1 plus CC. And that will be to the left, right? So let's say I put it at such a large value that it moves here. It essentially means that now it will have a 20 dB per decade roll-off. And after it hits the second pole, now it is going to have a 40 dB per decade roll-off, right? So you see, this is slightly better. The way I have drawn it, it is slightly better because the poles are far apart, but still the UGB falls after the second pole, right? So if you do this analysis and find that UGB falls after the second pole, then you probably have to increase the value of capacitance even further. And if you keep on increasing the value of the capacitance, so this plot is going to shift to the left, keep on shift. So I have not given enough space to the axis. So let's say, put the space here. So this guy is going to go even further left. So maybe somewhere over here is going to cross the UGB. And you get the idea now, right? So you keep on increasing the capacitance so that you hit the UGB around that 20 dB per decade mark. Okay. I mean, where you are still in the 20 dB per decade roll-off. So if you do that, then you are likely to get a phase margin of more than 45 degrees. Because if a second pole falls on UGB, then the first pole gives you 90 degrees, second pole gives you 45 degrees, 135 gone. You only have 180, 180 minus 135, that's 45-degree phase margin. Okay. So if you have a phase margin of 45 degrees, you can still get ringing, right? For phase margin of 45 degrees, that corresponds to 1 over root 2, right? Zeta over 1 over root 2. Know that or don't know that? Okay, so forget about that if you don't know that. So that's a piece of information which is not necessary for the purpose of this course. But all we need to know is, in order to get critically damped system, we want the P2 to be 4 times ahead of omega u, right? So if P2 is at 4 times omega, P2 equal to 4 times omega u, what is the excess phase? This is for critical damping. For two-pole systems. Right? So if this is the case, then you get minus pi by 2 because of the first pole. And for the second pole, you get P2 over omega u, which is minus pi by 2 minus tan inverse 1 over 4. So this roughly corresponds to 14 degrees. Okay. So the phase margin for a critically damped system is approximately equal to 76 degrees. So generally, if we want critically damped system, that is the fastest step response without overshoot, we try to hit a phase margin of 76 degrees. And that kind of is true even for systems with large number of poles also. Not strictly true. You can always design something where you can have phase margin of 76 degrees with a lot of poles and zeros, but it doesn't necessarily settle properly. But in most cases, most practical cases, this is okay, right? So that's what we tend to shoot for. Now, this can be done, but the issue is, as you can see, that in order to separate the poles by, let's say, 100x from each other, you need the capacitance to be also 100x higher than the other side, right? So when you are doing a breadboard design, which you will be doing in next semester in 380 labs, you will see that that is okay because the capacitance size doesn't really matter. Even if it's a 1 nanofarad capacitance or 10 picofarad capacitance, they all have the similar size, right? 2 leads coming out, you plug it in, they don't really matter. But in an integrated circuit, the capacitance are extremely costly. When I say costly, I essentially mean that they take a lot of area. And the area is directly proportional to the size. So a 1 nanofarad capacitance will be like 1,000 times more costlier than 1 picofarad capacitance, for example, in terms of the area it takes. So as it turns out, you cannot even make a 1 nanofarad capacitance in an IC. It's so big. It will take up the entire IC, 1 nanofarad capacitor. So then, because of these reasons, people had to come up with solutions where I can still get these type of responses, this type of pole splitting, but without using too much of chip area. Okay. So one trick to do that is the following. And the idea is extremely simple. So let's say you have an ideal voltage control voltage source, that is a VCVS of gain minus A. Okay. And you put a capacitor across it, value C. Now, if you apply a voltage here, let's say V test, what will be the voltage here? Minus A times V test. So what is the current that you are drawing through the capacitance? And note that it's a voltage control voltage source, no current goes into the amplifier. So what is that current that you are drawing through the capacitor? Voltage difference times the admittance. So basically voltage difference is 1 plus A times V test times the admittance, which is SC. So effectively now, if I say that this is a black box or an orange box, and I am looking into here, what am I seeing? I'm observing that I have applied a voltage V test, And this guy is drawing, has an element. I don't know what is inside, but this guy has an element, which is drawing a current of 1 plus A times SC times V test, right? So what does it look like then? This looks like a capacitance of size 1 plus A times C, right? If we had a capacitance of 1 plus A times C, it would have drawn in a current of 1 plus A times SC times V test, right? So using, now if A is, for example, 100, right? Then this mimics a capacitance of 100 times its size, or 101 times its size. The effective response, so essentially you are loading V test with a capacitor which is 100 times its physical size. Electrically, it's 100 times. Physically, it's still that small capacitor. So essentially, you break the trade-off, right, between large capacitance and large area by putting an amplifier in between. So this type of, this is often called Miller amplification or Miller effect. Okay, so once you want to do this, right? So if you want to do this, so I will provide this. You don't have to write it up. I will provide this PDF. So if you want to do this, so what you generally tend to do is forget about this GM2 here. So we had a second stage here, right? We had a second stage here. So you put a capacitor between the output of the first stage and the output of the second stage, because note that the second stage gives you the amplification, that minus A amplification. Okay. So if you do that, and I call this, now the second stage can be built in any way. It need not be a common source stage. It can also be a differential amplifier. But that differential amplifier need not be, I mean, if you don't need it, if one of the inputs of the second stage is grounded, then you can as well use a common source, right? Because in a common source stage, one of the inputs is the gate, other input is source. But the source effectively is, if the source becomes grounded, this is equivalent to a differential amplifier with one of the inputs grounded, right? So I can use as well a differential amplifier in the second stage, which we have been doing for till the end of the last class and a few minutes before today. So the key thing here to notice is that you can get Miller effect in this two-stage op amps, right, or two-stage structures. But the important thing to notice here is this is not a voltage-controlled voltage source, right? This is a voltage-controlled current source. So you are not going to get the exact expressions that you would have gotten if you had used Miller, if you had used a voltage-controlled voltage source, or the exact capacitances if you had used voltage-controlled voltage source. So since you don't get the exact thing, one needs to do a full-blown analysis to figure out what do you get. So this full-blown analysis is not a part of the course. I'll just take I will give you an intuition and get to the part which is a part of the course, right? You have which you can appreciate quickly. So if I do this analysis, this is basically again a two-port kind of thing. You have two different nodes. You write KCL, KVL, like the way we have been doing, just the terms are more complicated. So you come to this, and this is the loop gain expression that you get. Sorry, this is the loop gain expression that you get. It's a huge term, right? So now, nobody can make sense of this algebra. What is the intuition? You can advance that you can do. You can put it in MATLAB or in the simulator and see what comes. And then if it doesn't come what you want, then what to do, right? Then the job of the designer starts there, right? When you put everything in a simulator or something and nothing works, then you have to figure out what can you change to make it work. So in order to figure out what can you change to make it work, we start off with certain assumptions, or we start off with a need. The need is to ensure that this op-amp or this structure has a stable operation. When I say stable, I mean the poles are far apart. Okay. So in this case, you see this is a second order system. Two poles. Requirement is the poles are far apart if the system is working. Now, if the poles are far apart, then I can assume I can use these P1 plus P2 equal to minus B over A, P1, P2 is C over A for a second order system or second order quadratic, and use this approximation that P2 is minus B over A and P1 is minus C over B, right? So again, from this is A, this is B, this is C. So you do the algebra, and you get one expression for P1 and similarly another expression for P2. Now the question is, this P1 and P2 expressions are itself big, right? But what do I do with those? So we massage the expression slightly again, and we understand that the pole associated with this capacitor, pole associated with this node, right? Pole associated with this node should, in the absence of this capacitance, was GDS1 over C1 or G01 over C1. But if I put this capacitance, something changed, because of which we are getting these big terms, right? And we put this capacitance because we are expecting Miller effect. We were expecting large capacitances. We are expecting to use a small capacitance and mimic it, I mean, make it a large capacitance, right? So essentially, if everything is right, then we should expect the pole to be at GDS1 over a large value of capacitance, right? So this expression I would like to massage in such a way that in the numerator I get GDS1 and denominator I will see then what I get. Okay, so that's what we have done. So in the denominator, then in the numerator we have GDS1, and in the denominator what we see? We see one C1 term, which we expect. Okay, then we see this term. This is this capacitance C times 1 plus GM2 over GDS2. Now, what is GM2 over GDS2? This is the gain of the second stage, right? So this is A, that 1 plus A term came. So this is the A. So I'm getting this C1, I'm getting this 1 plus A. But because this is not this second stage is not a voltage control voltage source, I'm also getting some additional term. But as long as those additional terms are not dominant, I can neglect them and then close my eyes and say that this is still a Miller compensated two-stage. Okay. So as it turns out, as you can see, that whenever you get something like of the order of GM2 by GDS2, that will be the dominant term, right? Because that's the gain term. Everything else is of a one order magnitude lower. Because GDS1, GDS2 are of the same order, GDS1, GDS2 are of the same order. So essentially you get one dominant term at the denominator. So essentially this still becomes your new pole location is still at GDS1 over C1 plus 1 plus A2, where second stage is, A2 is a second stage gain times the C, right? Negative of that. So you still get that increased effective capacitance. That is good. You are able to save a lot of area. In fact, this is one of the very few structures where something even better happens, even with your asking for it. And whatever the better thing that happens is with regards to P2. Now, again, if you write those expressions, you get a huge expression, right? But again, don't want to look at that. I would like to massage it in such a way that it makes sense, right? It makes sense to a designer. So in this case, I'll start massaging it in such a way that the denominator makes sense, right? So in the denominator, effectively, a pole is some conductance over capacitance, right? If I know the conductance, then I stick to the conductance and see what is happening to the conductance. If I know the capacitance, then I stick to the capacitance and see what is happening to the conductance, right? So that's all. So in this case, if I'm looking at the output stage, the effective capacitance is C2 plus something extra. What is that extra? What is that extra? The extra is, looks like you have, what can you comment on this C1 by C plus C1? What does it look like? If I say equivalent capacitance is C times C1 over C plus C1, what does it imply? It's a series connection of two capacitors of value C and C1, right? It's a series, two capacitance of value C1, C and C1 put in series will give you an equivalent capacitance of that. And plus C2 means the C2 comes in parallel to that, right? So as you can see in this stage, I have a capacitance C2 and I have another C1 in parallel. So a series combination of C and C1 in parallel to it, right? So this denominator, that's why it makes sense, right? So it looks like I have something in the denominator which resembles whatever is put in the circuit. But what is happening to the numerator? The numerator has to be a conductance, right? So when I say a numerator has to be a conductance, I essentially mean that I should have a GDS2, definitely, because that is attached. That should be there. Fortunately, that is there. Now, what about this guy? Because anything that is multiplied with a GM would tend to be dominant, right? So what about that guy? So this is also you have done in one of the assignments without knowing it. So if I find out what is the if I ask you to find out what is the equivalent impedance of this structure, looking at the output node, what will I get? I am calling this C, right? So let me call this C in this case. So what will I get? So if this is V test, if I apply V test at this node, what will be this voltage? So if I apply V test at the output node, this voltage will be C by C plus C1 times V test, right? So I have a voltage division between these two capacitances, right? And what will be the current that I'll be drawing? GM2 times C by C plus C1 times V test. And I'll be drawing a current through this also. So effectively, the I test that I'll be drawing will be S times GM2 C. Sorry. So the I test that I'll be drawing inside the GM is effectively GM2 times C by C plus C1 times V test. And the current that I'll be drawing through C and C1 is CC1 by C plus C1 times S times V test, right? So essentially this becomes V test times one conductance whose value is GM2C plus C1 and one capacitance whose value is series combination of C and C1. So that should also make sense because this guy gives you the effective capacitance looking from the output side, and this node, this expression gives you the effective conductance, right? This conductance is, you are getting this conductance because when you excite something at the output, something at the same phase appears at the input. A voltage divided portion of the same phase appears at the input, which means you are drawing in a current at the same phase with respect to the voltage that you have applied, which means effectively this, even though you have two capacitances connected across GM, you are still getting a resistive current in, right? You are getting a resistive current and you are getting this capacitive current because the capacitance is already attached to it, right? So the key thing to note here is that the effective conductance out the output node has gone up because you are drawing an resistive current in. And the effective capacitance has gone up by this exact same amount, which is equivalent to the one that you are getting due to feedback. Okay. So essentially, now if you look at the top terms, the dominant term will effectively become this, and the capacitance will effectively become this. So essentially, your P2 becomes GM2C by C plus C1 divided. I'm neglecting all the non-dominant terms, and the denominator is C2 plus CC1 by C plus C1. Okay. And P1, because of Miller effect, so negative of this, Miller effect shifted to GDS1 by 1 plus A2 times C1. Or not C1, CC. So now you see that in the case of, in our case, where the P1 and P2 initially uncompensated of structure, where the P1 and P2 were initially located at the same place, after you compensated, P1 moved to the left because of this denominator getting magnified, and P2 moved to the right because the numerator got amplified, right? So P1 moves this side, P2 goes that side, which means I'm not only using a smaller value of capacitances, I'm able to get even pole splitting by pushing the poles in different directions. If you put a explicit capacitance, you are only explicit large capacitance in one of the node. You are only affecting it to push one of the poles to a lower frequency. You are keeping the effect of the other pole unchanged. But in this case, you are moving one pole to the left, other pole to the right. So essentially, you don't have to use a larger capacitance now, as large as you would have had to if you only had used one of the poles. Okay, so this is one of the characteristics of a two-stage Miller compensated op-amp. The other characteristics that I will not get into is for those of you who have been following, you will see that there is an explicit zero also, right? But it's a right-hand side zero. The right-hand side zero gives you a phase lag, right? A left-hand side zero gives you a phase lead. A right-hand side zero gives you a phase lag. Now, if you have a phase lag, and the thing is, you are getting a kind of, your magnitude response will go up, but you are getting phase lag. It's a double whammy in certain way, right? Your phase margin is going to get affected because of this extra phase lag. So that's why people tend to increase the values of GM1 and GM2. Tend to size GM2 in such a way that the phase lag associated with this extra zero is negligible, because the zero is at the zero frequency, as you can see in this case, is at GM2 over C. Right? So if you size, C is the Miller compensated op-amp, Miller capacitance. So you have fixed the Miller capacitance. If you have to push the zero at a higher frequency, you have to increase GM2, right? So that's how it is. So essentially, what are we ending up with? We are ending up with a structure which looks like this. So if this is a differential amplifier. The second stage, I am using a PMOS second stage. You can as well design it with an NMOS second stage. There's no harm. And you have something connected here, right? I'm only showing the DFAMP right now. And let's say this is C2, this is C1. And these are intrinsic capacitances associated with the device. In order to stabilize this, we are putting this extra capacitance CC or C, whatever. We have been using C, so let me keep it C. So this is the Miller capacitance. Now, note that we have CGD capacitances associated with these, right? Which we have been neglecting since the time we have been using, we have been introducing capacitances. Now you see that why am I neglecting? We had to anyway put CC, so that CGD will come in parallel to CC. So if at all, I probably don't have to use as high a value of CC as I probably needed in the first place, right? So in a certain way, this CGD capacitance of the second stage is probably not as critical if you are using a Miller compensated design. Okay, and the stuff. Now, how do I close the feedback loop? So obviously, if I want a gain of K, so I wanted K minus 1 R, this is R, this is the feedback voltage. Now, this feedback voltage can be connected either to this, let's say node 1, or to here, node 2. How do I know where do I connect? I do the same thing that I have been doing. Let's assume that this is connected here. Let's assume that this is connected here. Okay. So if then I go around, then I apply an hypothetical excitation and go around the loop and see whether the sense of the loop is correct or not. So let's do that. If this increases, this is going to decrease. If this decreases, this is going to increase. That increases, this is going to increase, which means it's not correcting. If it's not correcting, it is reinforcing, then obviously this is not true, the other is true. So it has to connect here. Okay. And so this is as far as how do you close the loop? Now, you also know that we only essentially have one current source, which we will be using, but we know how to mirror the current sources. So instead of this explicit current source, I will use a single current source. And here also, I'm going to use a current mirror, right? So this typically, what you end up with is a let's say I call it VI1, VI2. This typically is a structure that you see in books, which is called a two-stage Miller compensated op-amp. Okay. There are some more bells and whistles and additional stuff that you can add to it, but this essentially is what we that we shoot for. Okay. The only stuff that is remaining, which you will be able to appreciate very quickly, is the fact that when you apply, when things are working in negative feedback, you expect VI1 and VI2 to move up and down in unison, right? Because they are the error, the difference between the two is the error voltage. And the error voltage is supposed to be as low, close to zero, which essentially means that VI1 and VI2 are going to move up and down at the same rate, very close to each other. So if I do an open loop analysis of this structure, if I simply do an open loop analysis of this structure, assuming that VI1 and VI2 are moving up and down in the same rate, so that is, this is connected to each other, and you have instead of a current source, you have a transistor, and we know that this transistor has a RO, right? So then what tends to happen is, if these two voltages tend to move up and down, let's say this goes up by delta V, this goes up by delta V, right? So what can you comment on this voltage? Will this, in a differential operation, that voltage was zero, right? If one goes up, the other goes down, that operation is zero. But in this case, this voltage is also tend to go up because it's not differential. Okay, so I can make life simpler by saying that since these two stages are identical, I will split that resistance into 2R0, 2R0, right? And then I can draw a line of symmetry between them, because it seems like if this voltage increases, this voltage is also going to increase. If this voltage increases, this voltage is also going to increase by the same amount. So in that case, if I draw a line of symmetry, then this is not, no current will flow through them. If no current flows to them, I can as well do a half circuit analysis of one of them, and whatever happens in the left half will happen in the right half, right? So you know what's going to happen to this guy. We have done this analysis multiple times of the structure on the left, and the current that has, the voltage, the current that will flow here will be GM1, this is M1, M2, GM1 by 1 plus GM1 times 2R0 times delta V. And that will develop a voltage here with the effective impedance at this node is 1 over GM of the diode connected transistor. We have other GDSs, but we tend to neglect them because GM is a dominant term. So essentially, this voltage effectively becomes GM1 by GM3 times delta V by 1 plus GM1 times 2R0. Okay. And things get mirrored on the other side. And if you do the calculation, you will see that this voltage is almost equal to this voltage. So essentially, instead of this differential amplifier only responding to a differential input, it also responds to a common mode input also. By common mode, I mean that both the inputs are going up and down at the same rate. So this is one of the metrics to characterize a differential amplifier. What is the common mode gain with respect to a differential gain, right? So again, there is a technical term for it, but you don't have to bother. The technical term is CMRR. It's called common mode rejection ratio. Is the differential gain over the common mode gain, right? But that is a fancy way of saying that you evaluate the gain under two different conditions. You once put a differential input, find out the gain, put a common mode input, find out the gain, ratio of that. Ideally, you want the ratio to be infinity, but it'll never get infinity, higher the better, right? So this is how you go about designing it. Okay. So before we stop finally, I'll stop the recording here.